Hey everyone, welcome to my new vlog. I'm just kidding. This is 61BL walkthrough video of question number 2 from tutoring worksheet week 6. Yeah, it's gonna be about tree traversals. All right, let's get started. So if we read this question right, it says define a route to the leaf path as a sequence of nodes from the root of a tree to one of its leaves, right? Write a method, print some paths that takes in the tree node, T, and an integer K. And that prints out all the root to leaf paths whose values sum to k, right? So if we look at this example here, right, and our k is 13, we want to know which path from root to leaf. So there are 3 root to leaf paths here, right? Because we have 3 leaves. So this path, and this path, which ones are 13. And if it's a 13, then we just want to print that whole path out, right? So for example, here 10 to 5, that's 17, so that's a 13. 10 to 1, so that's going to be 13, right? And 10 for 1 is also 13. So what we want this function to print is 10 to 1, 10 for -1. Right, that's our ultimate goal. All right, let's take a look at our code here, right? So provide your solution in the code below. And obviously we have a function called print sum paths, right? And then we have a sum paths function. And it's clear that all the work, the most of the work that we have to do is going to be in here. All right. So let's fill in this wrapper, right? Let's just take a look at it. So it takes in T, K, and path, right? So we probably have to append something to like the path. But you know, I think we already can complete this, right? So we can just do T, K. All right, that's the easy part. So take a look at the function here, right? We want to create a function sum paths, and for some reason we like taken an empty string. So it's very likely that we will have to be appending like the path to it on the way down to loop, right? So that's like something that we have to like take care of when we're planning this function out, is that we're going to be getting in a string that keeps track of where we have been, right? So if we are 10, then we haven't been anywhere, so this string is empty, as we saw in this situation, right? It's an empty string. But for example, if we're 2, then we know we have to do like 10. And then at the end, if we are at the leaf and if it's 13, then we want to print out that whole string, right? So that's like really important to like take into mind. So as far as planning goes, we know what the function of string is, right? So now we have to like look into this function, and it's very likely it's going to be recursive, right? Because you want to keep going down to when you get to the leaf. Yeah. So now we have to like think about the different scenarios, right? And pretend we are at the leaf already. What is a leaf? A leaf doesn't have a child, right? It doesn't have a left or a right value. So then we have to take that into account when we're writing the code. So let's write that edge case here already, right? As we said, a leaf, you know, is the left is going to be empty, and the right is going to be empty, right? It doesn't have any kids. All right. So then we know it's a leaf. And what do we want to do at the leaf, right? So we have 2 scenarios here what we can do at the leaf. So 10 to 5 is 17, and which is not 13. So even though it is a leaf, we don't want to do anything because it doesn't sum up to 13, right? But what about 10 to 1, right? That's 13. That is our k value. So we want to make sure that our k value is equal to a certain value. But we will leave that empty here because we haven't implemented yet. So something has to do with k. All right, and we'll have to fix that later, right? And then we want to print it out, obviously. So we do system.out. And what do we want to print out? As we said earlier, path is probably going to contain some kind of recursive like structure of making sure that like or where we've been is going to be printed out. So we can do something like path, and right, obviously you want to also print out yourself if that's the situation. So that's why we're gonna append, or you're gonna like append your own value to it, right? As a string. All right, we got that base case out of the way. Now let's take a look at what we're gonna do in the other situations, right? In the other situations, it's not a leaf at all. It can have a kid on the left side, it can have a kid on the right side, it can have a kid on both sides, right? But we want to make sure that for each of those kids, when we get to leaf, we want to check if that value reaches k. Right? Okay, let's take a look at that. So we want to check if there's something on the left, right? So we have two scenarios I said, or three scenarios as I said earlier, that it can have a kid on the left, it can have a kid on the right, but it can also have a kid on both sides. It's very easy. We can just account for that in two if statements, right? So we can test if the left side is null and if the right side is null, and we just call the function recursively on that. So let's write that down here. I'll give another color just like to make it a little more clear. If t.left, and we want to make sure that that is not null, right? Because if that's not null, then we want to do something on that branch until the end. We'll do something, and if right is null. Then we want to do something, right? All right. And as we defined earlier, right, this is a recursive function, right? So we're going to call the function itself on it. So some paths. But what are we going to call on it? That's really interesting what we want to do, right? So t is the node itself, and t left is where we're going to call this function on, right? So the node that we're going to call it now on is t.left in this situation. And then the next value is k, right? So if we are 10 to 5, right, what we want to do here is we want to check if this value down here is 13, right? But what if we're at 2? Like, or you have to like keep track of it, or you can just subtract 10 from it, right? So if you have k is equal 13 and you subtract 10, the only thing you need to check is that like down to the leaf, you get to 3, right? Which is not the case here, but is the case here. So what we're going to do here is we're just going to subtract k minus the value of yourself from it. All right. And then we want to use the path, but we want to append your own, where you are now, you want to append that to it, right? Because, yeah, you just want to like append where we have been since when we went like one depth down, so we want to append one node to it. So when you happen here, you want to append path plus t dot value as well. I think it's a space, right? Yes, so space plus t dot value. And close it. All right, and then for right, it's going to be exactly the same, but then for the right situation, some paths t dot right k minus t dot value path plus t dot value as well. Yeah, so we have almost accounted for everything, right? But we have not accounted for k yet. So what we said is earlier, we're just going to subtract all the way down, right? So for example, if we're going to take this right down, we subtract 10 from 13, right? So for example, k is 13, we subtract 10 from here. So k here is going to be equal to 3, right? When it reaches 4, it's going to like get to 3. And then when we reach down here, it's going to be -1. So the thing that we need to do is to check whether the value of k is equal to the value of your leaf node, which is the only thing that we need to account for here still, right? So then we set k equals to, or check if k is equal to the value of your leaf node. Right? And if it reaches down to 5, then it doesn't do anything because there's no like statement here, right? Because like it doesn't do anything, right? So when it reaches 5, it doesn't have a left or like a right kid. So it just, this is like void, like it doesn't do anything. And this is not being evaluated at all. So it just stops. And if it does end up to 13 or to like the value k, like if the path sums up to k, then what we're going to see is that the value k is equal to the value of the leaf here, and then we're going to print out the whole path, right? Yeah. All right, let's jump to question B. So what is the worst case runtime of print sum paths in terms of n, the number of nodes in the tree? So we want to think of the worst case scenario with respect to like the number of the nodes of the tree, right? And a really bad tree, I think all of you guys remember that a linked list is also a tree. It's just a really inefficient tree, right? So if we had, for example, this tree here, I don't have much space here. Let me create a new page. All right, so what if worst case runtime? And right? So what if we had a really bad tree, like a linked list, that just kept going down, right? If you have n nodes. What is the worst case runtime for this situation? Well, we need to check all the nodes in our tree, right? We have to go all the way down. And how many items does our string value, right? Because we have to keep track of our string. Like each time we add one to it, right? Like one item to where it has been, right? So in this situation, it hasn't been anywhere. In this situation, 1, and I will just number them, right? I will like enumerate them 1, 2, 4, and to n, right? What is string going to be at 2? At 2, our string is going to be 1, right? At 3, it's going to be 1, 2. And then it grows all the way down, right? It goes all the way down like linearly per operation. So at some point, we're going to have a whole string called 1 to n, right? So each string concatenation itself is linear. But if we're going to sum up all the work that has been done, we get something like this. And I think it's really familiar, right? And I always forget, like, if you like have like a big like sequence of like big sum, right? Then it's really weird. But what I always remember is that you have like a bar of 1, 2, 3, 4, 5, and then up to n, which is n and then 1 n, right? So it's like a triangle. So it's like a half, because it's a triangle. If we calculate the area, you have a half n times n is a half n squared. And we know that this is equal to O of n squared, right? So similarly, what we have here is 1, 2, 1, 1, 2, 1, 2, 3, and then up to 1 to the n, because we're concatenating those strings, right? So in this situation, the worst case scenario of the work that's been done is theta of n squared by, since like if we add up 1, 2, 3, 4 to n, you get n squared, right? So that is when we account for the number of nodes. But what if you're gonna account for like the tree, right? Like what happens to like the amount of work if we have to like evaluate in terms of the tree, worst case. So a tree, like worst case scenario, the height, if we're gonna evaluate it in height, right? When the most work is done for a tree is when it's a complete binary tree, right? So the complete binary tree of h, of height h. All right. And how many leaves do we have? Well, we have 2 to the h leaf nodes, right? And what we said earlier, right? Each string concatenation is h amount of work. It's linear, right? So what we can do here is theta of h times 2 to the h work, if we're going to express it in terms of the height of the tree. All right, thank you for watching this video. And make sure to watch the other videos in the playlist for the other questions on the worksheet. All right, see you guys around.